A physicist studying black holes found that in an expanding universe, Einstein's equations require the expansion rate at the event horizon of every black hole to be constant, meaning it's the same for all black holes. This implies that the only energy present at the event horizon is dark energy, known as the cosmological constant. The study was published on the arXiv preprint server. Nikodem Popławski, a distinguished lecturer at the University of New Haven, said, otherwise, the pressure of matter and the curvature of spacetime at the horizon would have to be infinite, but that's not physical. Black holes are fascinating because they involve the simplest things in the universe. Their only properties are mass, electric charge, and angular momentum spin. Yet, their simplicity leads to the fantastic feature of an event horizon at a critical distance from the black hole, a physical, though in the simplest case, spherical surface. Anything closer to the black hole, within the event horizon, can never escape. Black holes were predicted in 1916 by Karl Schwarzschild, a German soldier suffering from the painful autoimmune skin disease pemphigus while serving on the Russian front. Using Einstein's general relativity equations, he assumed a massive, non-rotating, perfectly round object in an otherwise empty and unchanging universe and discovered the event horizon. The radius of the event horizon is proportional to the black hole's mass. Inside the horizon, not even light, the fastest thing in the universe, can escape the hole. Schwarzschild also found a notable singularity at the black hole's center, a point of infinite density where Einstein's gravity laws appear to break down. Since then, astronomers have found that most galaxies contain a supermassive black hole at their center. For the Milky Way, its Sagittarius asterisk, which is over 4 million times the mass of the Sun, a black hole in the center of the Messier 87 galaxy, located 55 million light-years from Earth, surrounded by a halo of light, was directly imaged only in 2019. Popławski went beyond Schwarzschild by assuming a massive, centrally symmetric object in an expanding universe. In this scenario, Einstein's equations for the structure of spacetime around the mass were first solved in 1933 by British mathematician and cosmologist George McVitie. McVitie found that spacetime near the mass has an event horizon similar to Schwarzschild's, but far from the mass, the universe expands, just like our universe. The Hubble parameter, also called the Hubble constant, indicates the rate at which the universe expands. Using McVitie's solution, Popławski found that the expansion rate of space at the event horizon must be constant, related only to the cosmological constant, which can be interpreted as the energy density of the vacuum of spacetime. Today, we know this as the density of dark energy. So, the only energy at the horizon is dark energy. As a result, different parts of the universe expand at different rates. In fact, a similar thing has been found in the Hubble tension, a statistically significant discrepancy between the measured values of the Hubble parameter, depending on whether late universe or early universe measurements, like cosmic microwave background radiation measurements, are used. Popławski said this inconsistency in his study is a natural consequence of a correct analysis of the spacetime of a black hole in an expanding universe within Einstein's general relativity theory. Moreover, his equations show that the value of the cosmological constant, and thus dark energy, must be positive as a result of the universe expanding at different rates. Otherwise, Popławski said, without this constant, a closed universe would oscillate and could not create cosmic voids. It's the simplest explanation for the observed current acceleration of the universe. Imagine the universe expanding on the surface boundary for a star, but the object itself isn't expanding because it's gravitationally and electromagnetically bound. However, the event horizon is a mathematically abstract thing. It's not made of matter or energy, just points in space, so it's not surprising that space has a constant expansion rate there. The event horizon itself, and therefore a black hole, isn't expanding. The points of space outside the horizon are moving away from it. Real black holes spin, but if the spin is generally slow, Popławski's conclusions should apply to them as well. However, measuring the Hubble parameter at the event horizon is currently impossible unless new techniques are developed.